You might be familiar with the concept of infinity. You might know that infinity is not considered a number, but rather it is considered a concept, something without end. But despite it not being a number, that doesn't mean that it isn't useful. In many cases, infinity can be used as you would use a number. In fact, infinity can be used to describe finite quantities. To understand how, let's say that there is a wall 1 kilometer away from you that you want to walk to. First, you walk half a kilometer and then you rest. And then you walk a quarter of a kilometer and then you rest. And then you walk an eighth of a kilometer and so on. The distance you walk after each rest halves each time. So the question is, will you ever reach the wall? At first glance, this might seem kind of obvious. You must reach the wall at some point, right? It's only a kilometer away after all. However, the distances of the walks you take shrink fast enough that no matter how many walks you take, it will always be a very tiny distance away from the wall. What this means is that if you take an infinite amount of walks, you'll reach the wall. But that makes no sense, right? If you take an infinite amount of these walks, then you must travel an infinite distance, right? Actually, no. The distance of these walks shrink fast enough that an infinite amount of them would add up to a finite quantity. This quality is called convergence. At first, it might seem quite absurd that an infinite quantity would add up to a finite number, and it might feel very wrong to be working with infinity so intimately. And the people who first described this sort of thing felt the exact same way. This conundrum is called Zeno's paradox, named after Zeno of Elea, who was a Greek philosopher who first described such a question. At the time of Zeno, concepts such as infinite sums leading to finite numbers like we just described were considered absurd, and were used as evidence to show logical contradictions in a lot of philosophical models. However, Zeno was wrong. This paradox is naturally paradoxical and doesn't show anything. The sum of the series 1/2, 1/4, 1/8, and so on does add up to a finite number, and that number is 1. Now, let's try to see why this is. First of all, let's quantify what we just described, aka Zeno's paradox. It can be represented as the sum of all the numbers 1/2, 1/4, 1/8, 1/16, and so on, with the number halving with each iteration. Essentially, each number in the sequence is half of the number before it, and you're adding up all of the numbers in the sequence. Now let's try to see why the sum of the series is 1. What we could do is we could first construct a square with the side length 1, and this square has an area of 1. Now let's try to show half of the square. This new section has an area of 1/2. Now let's show a quarter of the square, this having an area of 1/4, then 1/8, 1/16, and so on forever. You'll see that since each section is half the one before it, a pair of consecutive numbers in the set form this sort of step shape. And since there are an infinite number of numbers, there are an infinite number of such step shapes. An infinite number of such step shapes will fully fill the square. The area of the square as a whole is 1, and therefore the sum of these shaded regions is 1. Each shaded area constitutes a number in the series we talked about, so the sum of the shaded areas, which is 1, is equal to the sum of the series we talked about, meaning that the sum of the series we talked about, which is 1/2, 1/4, 1/8, and so on forever, is 1. Even with this concrete result, it might still seem unnatural to be working with infinity like this. Nonetheless, I hope this example gave you a good intuition for why infinite series makes sense. This infinite series shrinks fast enough for its result to be a finite number. That is the core idea of infinite series. I also want to give you a subtle but different type of understanding for this sort of thing, which we'll call limits. What we're talking about can be thought of as with the sequence 1/2 plus 1/4 plus 1/8 and so on gets closer to the more terms we add. 1/2 plus 1/4 equals 0.75. 1/2 plus 1/4 plus 1/8 equals 0.875. The more terms we add to the sequence, the closer the result gets to 1. This is exactly what a limit is. We've learned about infinite sequences that sum up to a finite number. However, not all infinite sequences of numbers will sum up to some finite number, especially not the ones that don't shrink. Take the series 1 plus 1 plus 1 plus 1 and so on. This sequence is just an infinite amount of ones, and the series does not shrink, and therefore it does not converge to anything. It just diverges to infinity. This quality is called divergence, and there are series that shrink and are divergent, like 1 plus 1/2 plus 1/3 plus 1/4 and so on. This series does diverge to infinity, but it's not immediately obvious that it diverges, and it is a bit hard to prove so. Just as a notice, I wanted to clarify that this is a video meant to be a base level introduction to infinite series as a concept. We've explored convergent series and divergent series and the intuition surrounding them. However, in mathematics, there's a very important distinction to be made between rigor and proof and intuition. What I've tried to provide in this video is intuition, but the rigor of this topic does require more complex tools. Rigorously defining infinity is notoriously hard. Remember the limits from before? That is one of the ways we can more precisely define infinite series. And that's the end of the lesson. I hope that you learned something new today about infinite series and infinity in general. Thanks for watching.